All right, hello everyone. Today, we're gonna start AP Calculus. Um, I guess AP Calculus review. This is a worksheet. It's called AB Calculus Path to A5 Problems. It's a list of all the important concepts or topics that will be in AB Calculus. And the first thing we're gonna dive into is limits. So we're gonna cover number 1, number 2, number 3, number 4, number 5. Definition of a limit, one-sided limits, horizontal asymptotes, and limits at infinity, vertical asymptotes and infinite limits, the weird limits, and continuity at a point. So before diving into this unit, I guess unit 1, I want to show you guys what a limit is. This is just a more basic definition, I guess. It's from English to mathematics. Let's say it in English first, okay? So f of x gets close to some limit as x gets close to some value. When we call the limit L and the value that x gets close to a, we can say that f of x gets close to L as x gets close to a. And this will make sense once we dive into it. So the first thing we're going to do is definition of a limit. Alright, so here's the first one, definition of a limit. The intended height or y value of a function f of x. Remember that the function that doesn't actually have to reach that height, and as the limit as x approaches c of f of x, and it's approaching from both sides. Right there, the limit of f of x as x approaches c is expressed as that. So methods for finding a limit, you're gonna direct substitute the values into the function or look at the graph. Some reasons why a limit will fail to exist is that the function approaches a different number from the left side than from the right side. The function increases or decreases without bound, or the function oscillates between two fixed values. Alright, so number 1, evaluate the limit as x approaches 3 of the function 2x squared plus 7x. So first we're gonna direct substitute the value. So we're gonna plug 3 into x. So the limit as x approaches 3 of 2x squared plus 7x. We're gonna plug 3 into our x value. So it's gonna be 2 times 3 squared plus 7 times 3, which should give us 18 plus 21, 39. And that should be our answer. So the limit as x approaches 2x squared plus 7x is 39. It's approaching 39 from both sides. Next, number 2. Find the limit, if it exists, of the limit as x approaches negative 2 of the absolute value of x plus 2 over x plus 2. Okay, so same thing. We're going to direct substitute. The limit as x approaches negative 2 of the absolute value of x plus 2 over x plus 2. Plugging that in, will be negative 2 plus 2 of negative 2 plus 2, and that just simply gives us 0 over 0, which is d and e. There's no need for L'Hopital's rules or anything else. It's simply d and e. Number 3, use the graph below to find the following limits. So we have this graph that represents h of x, capitalize h of x. So now we need to find the limit as x approaches a of h of x. So we're approaching a from both sides, so getting closer to a from the left, and we're getting closer to a from the right, and it looks like it's approaching 1. Our answer should be 1. Okay, letter B, the limit as x approaches b of h of x. Okay, so same thing, I'm going to do this in a different color. So we're approaching b from the left, and we are approaching b from the right. Looks like they're not approaching the same number because this is a jump, and a jump is a non-removable discontinuity. So it's discontinuous at letter B. So our answer should be D and E. Because from the left it's approaching like 0.7, and then from the right it's approaching like 2.7. So those are obviously not the same. So D and E. Okay, so I hope so far that's pretty easy. Limits are usually the easiest units, hence why it's the first. So now we're gonna move on to one-sided limits. So now we're either gonna go from the right side or the left. So the limit as x approaches c from the right of f of x, literally means the limit from the right. This plus sign means it's approaching c from the right, so that's important. Plus right, okay. And then the limit as x approaches c from the left, so this minus sign. Is left. Okay. A curve has a limit if and only if both sides are equal to each other. So from the left side and the right side are equal to each other. A curve is continuous on a closed interval AB if it is continuous on the open interval AB and the limit exists and the limit is equal to f of the value of the function. The limit at the endpoints has to match. So in order for it to be continuous, it has to meet 3 criteria, I guess, or 3 requirements. It has 3 requirements. First one, the limit has to exist. The limit must exist. In order for the limit to exist, both sides have to equal to each other. So right here. Second one is the value of the function must exist. So f of whatever value must exist. Equals to a. Let's just say a. And then the third one, the limit as x approaches c must equal to, or forgot, of the function must equal to f of c. So this will make sense in a bit. So first one, use the graph to write the use the graph to the right to find the following limits if they exist. Alright, so number 1, the limit as x approaches -3 from the left. Remember, the negative sign means left. So if we go over to -3, it's right here. So we're only worrying about the left side as x approaches -3. So it's getting closer to -3 from the left, and it looks like it's approaching -5. Okay. Number 2. All right, this time it's from the right side. So now we're gonna go up, focus on the right side. Looks like it's approaching 2. So our answer is 2. Okay, number 3. The limit as x approaches 0 from the left of g of x. So now we're gonna move on to 0. 0 right there. And I think it's, oh yeah, from the left. So as x approaches 0 from the left, it's approaching -4. Okay. Next, g of -3. So let's move on to -3. There is no g of -3. Oh, actually, never mind. There is. My bad. This circle dot right there, the closed circle, meaning that's where g of -3 exists. So it is -5. The open circle meaning it's there's no value there. It does not exist. Just a reminder. Number 5, the limit as x approaches -6 from the right of g of x. Let's see, where's -6? Okay, so -6 right here, and it's from the right. So we're approaching -6 from the right side. It looks like it's approaching -5. Next, the limit as x approaches -6 of g of x. So it's going from both sides, but there's no both sides. There's only the right side. So we can say that it does not exist. Next, the limit as x approaches 0 from the right. So from the left, we got -4. And from the right, it's also approaching -4. So our answer is -4. It's getting closer and closer to -4. Didn't we already answer that? Okay, the limit as x approaches -3 of g of x from both sides. Well, this is a jump, and a jump is discontinuous, so there's no limit. So it's D and E. Next, the limit as x approaches 0 of g of x. This time it's from both sides, and well, from the left it's approaching -4. From the right it's approaching -4, so -4. Alright, and that's it for one-sided limits. I hope that's easy. Alright, next we're going to move on to horizontal asymptotes and limits at infinity. I think this one's like one of my favorites. Pretty easy. For horizontal asymptotes, if f of x approaches c as x approaches positive or negative infinity, then y equals c is a horizontal asymptote. A horizontal asymptote describes the behavior at the far ends of the graph. It is helpful to think of an end behavior function that will mimic the given function. What will dominate as the x values get larger in both directions. Okay, and then the limit at infinity. Graphically, a limit at infinity will level off at a certain value on one or both ends. Analytically, which means doing it by hand, find an end behavior function to model the given function, then use direct substitution to evaluate the limit. So the main thing to take away is this part, the shortcut. Just worry about this. And also worry about this. So if the top is heavy or top heavy, the limit is D and E. If it's bottom heavy, the limit is equal to 0. And if it's equal to each other, the limit is equal to the ratio of leading coefficient. And we're talking about the exponents. The highest exponents. We're talking about that. And please be careful with the shortcuts. Some function acts strange and requires some extra thought. Also watch out, or watch our, out for limits at negative infinity. They can require extra thought. Alright, so let's go on to number 1. So the limit as n approaches infinity, 4n squared over n squared plus 10,000 n. So we only care about the exponents. So we're only going to worry about these, the 4n squared and the n squared. And if we go back up to our shortcut, it is equal, since n squared, since there's an n squared for the numerator and there's an n squared in the denominator, they're equal to each other. So we're only taking the ratio of the leading coefficient, which is the number in front of the variable. So 4n squared over n squared. In front of n squared is 1. There's an invisible 1. So we only care about 4 over 1, and then it's 4. So we have a horizontal asymptote at y equals 4. Next, the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1. So we're taking our the highest exponent in the numerator, which is 2x, and then the highest in the denominator, which is 3x squared. And it looks like they're not equal to each other. So let's go back. Scroll back up. Let's see. It looks like it is bottom heavy, since 3x squared is I guess bigger than 2x or greater than 2x. So since it's bottom heavy, the limit is equal to 0. So there's no or the horizontal asymptote is 0. Y equals 0. That's the answer. And also, you can double check by plugging these functions into decimals and check the horizontal asymptote. That's a good way to check if you're on the right track or if you got the right answer. Highly encourage that. Okay, next. The limit as x approaches infinity of 2x to the power of 5 minus 7 over negative 5x squared plus 9. So we only care about the highest exponent in our numerator, which is 2x to the power of 5, and the highest exponent in our denominator, which is negative 5x squared. So we're going to write that out. Okay. So Once again, the exponents are not equal to each other, so let's scroll back up. Looks like it is top heavy since the 2x to the power 5, since the 5 is greater than the 2 at the bottom. So it is D&E. Let's do the 4 and 5. Let's see. Okay. Let's move on to number 7. For x greater than or equal to 0, the horizontal line is y equals to 2, is an asymptote for the graph of the function f. Which of the following statement must be true? So we have a horizontal line of y equals 2. Okay, so let's see. F of 0 is equal to 2. That could be true, but it could not be true as well because there could be a hole there. But the keyword is must be true, meaning it will always be true. F of 0 is equal to 2. That's possibly, it could be, but there could also be a hole there, so that's not our best option. F of x is not equal to 2 for all x greater than or equal to 0. That is false. Not all, because it's approaching 2, because 2 is our horizontal line, so that's not right. F of 2 is undefined. It could be, but it could also be approaching 2. So C isn't our best choice. The limit as x approaches 2 of f of x is equal to infinity. I think that's wrong because we have a horizontal line at y equals 2. I feel like our answer should be E, because as x approaches infinity, it approaches 2, because our 2 is our horizontal line. So if I draw a graph, it'll be something like, I'm just gonna draw a random thing. See, that's gonna be our y equals 2, and as x as we approaches infinity, for our x value, it's approaching 2 for our y values. Okay, now we're gonna move on to vertical asymptotes, infinite limits. So if f of x is if f of x is approaching positive or negative infinity as x approaches c from the left or the right, then x is equal to c is a vertical asymptote. Your function has a vertical asymptote, then it is not continuous. Vertical asymptote is it's pretty much like infinite discontinuity. So yeah, vertical asymptotes occur where the denominator is equal to 0, there is no common factor, and the numerator does not equal to 0. So graphically, an infinite limit increases or decreases without bound at a vertical asymptote. And analytically, direct substitution yields a 0 in the denominator only with no common factor or indeterminate form. Numerically, substitute a decimal number approaching the limit to see if the y value is approaching positive or negative infinity. Alright, let's get started. Like I said, the best thing is use decimals if you're allowed to. It helps. But I'm just doing it algebraically, or I guess analytically. So let's do this. So number 1, g of x is equal to 2x squared minus x over x plus 5. So now we need to find the vertical asymptotes and include intervals where the function is continuous. So this is Algebra 2 or Algebra 1 question. So to find our vertical asymptote, we only care about the denominator, so x plus 5. So we're going to set x plus 5 equal to 0 and solve for x. X is equal to negative 5. So there's a vertical asymptote at x equals negative 5. So that's the first part. For our answer, as you can see, there's a VA at negative 5. So we're gonna go for negative infinity to negative 5. Close the bracket. Union negative 5 to positive infinity. I think it's parentheses, not bracket. Okay, and then that's the same thing for number 2. To save time, I guess you guys can do that. Alright, now we're going to move on to calculus. The limit as x approaches 1 from the right and the left. We need to find that. So let's see. Oh, okay, so the limit as x approaches 1, and that's a horrible arrow, approaches 1 from the right of this function. So all we have to do is plug in a number from the left, or sorry, from the right of 1, so like 1.001 into the function, plug that in. So 1.001 squared plus 5 times 1.001 over 1.001 minus 1. 1.001 minus 1 is 0.001, which is it's a very small number. So I think our answer will be positive infinity. And you can just plug that in. You'll get like a giant number, not giant, but like a really big number. And then that'll just be infinity. And also I learned, I was taught that infinity is not a number, it's a concept. So that's very important to know. So plugging that in, 1.001 squared plus 5 times 1.001, and then over 1.001 minus 1. You get 6,000, so we're just going to say that's infinity. Alright, number 5. I guess we'll do 5 as well. Oh, wait, I forgot. We got to do from the left now. So the limit as x approaches 1 from the left side of y, the function y. So now we have to pick a value from the left of 1. So we'll go with 0.999. All over 0.999 minus 1. We don't care about the numerator. It'll just be a number. Sorry, that's a horrible. It'll just be some number over the denominator, which we really care about that. So 0.999 minus 1. It's going to be a negative small number. Let's see. What is... Hold on. I think it will be like 0.000. Okay, and that will just give us negative infinity. So the most important thing is a big number divided by a very small number, so like 0.00 something, like that's a very small number, it will give you a really big number, which will be positive infinity, and vice versa for a negative denominator. Same thing, except it'll just be a negative sign in front of it. Okay, we're gonna move on. I'll let you guys do that one. Ooh, we're gonna move on to the weird limits. So these are all the, I guess, weird limits you'll come across. I think it's okay if you don't memorize all these. It's definitely important to be familiar with them in case you ever come across these types of problems. So like the first one, the limit as x approaches infinity of e to the power 1 over x. So we look at some of the functions they gave us, or some of the limits they gave us. Let's see which one matches with this problem. Okay, so actually we can go with this one right here. So the limit as x approaches infinity of e to the power 1 over x. So we know that the limit as x approaches negative infinity. Am I looking at the right one? Oh, it's the same thing. It's actually this one, but it's the same thing as from the right, or from negative infinity. Okay, so let's just pay attention to this one, the positive infinity one. So we know that the limit as x approaches infinity of 1 over x is equal to 0. So it's the same thing as for this problem. So just be e to the power of 0, which is anything to the power of 0 is 1. We still don't know if 0 to the power of 0 is 1 or d/e. It's still an ongoing debate right there. I'm not going to say anything about that. And then the rest are the same like that. Just look at these given limits. Continuity at a point. So like before what I said, or just like before I said, there are 3 requirements that need to be met in order for the function to be continuous. Is that f of c exists, meaning that function has a y value for the x value in the question, and the limits from both sides exist, and the limit must equal to the function's value. So number 1, state how a continuity is destroyed at x equals c for each given, or for each graph below. So already, number 1, there's a jump, right? There's a jump. It is non-removable. It is discontinuous at x equals 1. So we can say it is a non-removable discontinuity there. But the most important thing is there's a jump, so it is discontinuous. Number 2, it is discontinuous at x equals 2 because it is a removable. There's a hole, but it's also a removable discontinuity. And what I mean by removable is I believe it's you can replace this open circle in for the closed circle. So, and then number 3, same thing to number 2, except there's no closed circles, so we're not gonna assume it's removable or non-removable. So it's there's an open circle, meaning there's a hole. It is not continuous. And then let's see if we should do 4 or 5 or 6. This video is pretty long, I think. So Alright, I guess we'll do 4 then. I think this one's the easiest. We can get this one done. If the function f is continuous and if f of x is equal to x squared minus 4 over x squared, x plus 2, when x is not equal to negative 2, then what is f of negative 2? Okay, so we need to find the limits from both sides, and the limits must equal to f of negative 2. Okay, and it says it is continuous, so we need to make sure we meet the 3 requirements. So the limit as x approaches negative 2 from the left of x squared minus 4 over x plus 2. And if we plug that in, it's going to give us 0 over 0, which is not good. That's an indeterminate form. So, but we're not done there. We can simplify this function. So we can just do the limit as x approaches negative 2 from the left. And then the x squared negative 4, we can factor that. So it can be x plus 2 and x minus 2 over x plus 2. And we can cancel out, or we can get rid of x plus 2. So it'll just be x minus 2, and then a value from the left of negative 2. Plugging that in, we'll get like negative 4. It's going to be about negative 4. And then if we do the same thing from the right, we're not going to use the x squared minus 4 over x plus 2. We're going to use the x minus 2. Because if we plug that in, we'll just get 0 over 0. So using this, we'll get around negative 4 as well. Since the limits are from the right and left are the same, the limits exist, meaning f of negative 2 must equal to negative 4. So that's 1 right there. The limits exist. And then the third requirement is f of negative 2 is equal to the limit as x approaches negative 2 of f of x, which is equal to negative 4. So that's how you prove or make sure the function is continuous, is by these 3 requirements. Very important. Yeah, that's it for Unit 1. Or at least these are the most important thing from Unit 1. And then make sure to comment if there's anything wrong or If I made a mistake or if you need a better explanation, I can try my best to help. And I'll see you guys next time for Unit 2, which we will cover, let's see, the average rate of change, instantaneous rate of change, tangent line, horizontal tangent line, linear approximation. I think that's all. And then the rest are Unit 3. Alright, I guess see you guys next time for Unit 2. Have a good day.